Alright guys, let's get started. So before we get into transformations with sine and cosine, let's just do some review about transforming with other functions that we're more familiar with, okay? So I'm just going to call on Emma and say, Emma, you can choose any of these. Tell me what one transformation from any of these. Boom. 5. If we add 5, that just takes our x squared, which is u, and goes up 5. Great. Let's go to David Espinoza. Tell me just something else. Yes, great. We call this a vertical stretch. So we're going to stretch it vertically by a factor of 2. Awesome. Antonio, tell me another one. You tell me. What do you guys think? It's the right, because in the inside we do the opposite. Good job knowing it was horizontal, and then it's to the right, 3 things. Antonio? Alright, so that was our transformations here. If we're timesing on the outside, it's a vertical stretch. Adding or subtracting on the inside is left or right, you do the opposite. Adding or subtracting on the outside is vertical shifts, and you do whatever it tells you to do. Let's jump now to, let's do this one. It's going to be pretty similar here on this one. Ruby, can you tell me something on there? Up 6. Jay, tell me something else. Vertical stretch of 3. Awesome. And then Louise, tell me, what is that minus 2? It's going to be like this, except it's on the exponent. So what would that do? It's actually going to be to the right 2 because you do the opposite. And when we see negative, we think left, right? But it's actually going to be to the right because we do the opposites if it's inside. In this case, it was inside the exponent, so we don't see the parentheses. So it's a little bit tricky. But good job, we got that. Last one. Let's just open it to a class. If you have a negative on the outside, what does that do? It's going to flip it over the x-axis. Nice job. And this minus 3, we know what that does. What does that do? Down 3. Now, this is one that we maybe mentioned briefly, but we didn't do a whole lot of. What about timesing on the inside? If timesing on the outside is a vertical stretch, what do you think timesing on the inside is going to do?
Horizontal stretch.
Yes, good job, guys. Now, here's the thing that's going to be tricky with the horizontal stretch. You actually don't stretch it by 2. You stretch it by the reciprocal of 2. Do you know what the reciprocal of 2 is? If I flip 2 over, what do you get?
1/2.
So it's a horizontal stretch by 1/2. Now we're going to see that same thing as we've switched to trigonometric functions. When I say trigonometric functions, that's fancy for me just saying when you're graphing sine and cosine. Technically, tangent has its own graph. We're not going to graph it. We also have, yeah, tangent does, so does secant, cosecant, and cotangent.
Does it look like these ones?
No, it actually makes a bunch of Slytherin snakes.
What?
But don't worry about it. We're not going to get too much into that, okay?
Oh,
So guys, when we see this, and this isn't in your notes, don't worry about it, but when you see this, you might at first be scared and be like, oh, I don't like it because of the sine and the theta. But guys, it's going to be the same idea. What is timesing on the outside going to do? What is this 2 going to do?
This 2 is going to...
There we go. It's a vertical stretch. Timesing on the outside, or adding on the outside, which way is that going to move it? We're going to go up 1. And then we just talked about that timesing by 2 on the inside. What do we call that? Horizontal stretch. But that's not going to be by 2, it's going to be by what?
1/2.
Great job. Now what we're going to do is with trigonometry, they decided, let's give these things different names. It's the same idea, just different names. We're going to call the vertical stretch here amplitude. And we talked about, we defined that last time as a distance from the midline to the max. But now our amplitude, we're just going to think of it as how much we stretch it out. And it's the same definition. This horizontal stretch is going to influence our period, which is the length of a cycle. When we are graphing plain old sine and cosine, the length of a cycle is 2 pi. We derived it by going around the unit circle 1 time, which was 1 rotation in radians is 2 pi. Lastly, when we go up 1, what that's going to change is it's going to change where our midline is. Our midline is normally at 0, that's the middle, right? Our max is 1, our minimum is -1, the midline's right in the middle. But if we shift everything up 1, then our new midline goes from 0 to 1. Okay, let's go to this next one here. This just has something that the other ones don't have. So what would we call 3? Instead of saying that's a vertical stretch, we're going to call that the amplitude. And then here, that -2, that's going to make, we're going to move that down 2, and that's going to become what?
The new midline.
The new midline.
And pi is our period, right?
No, because look here, we're not timesing, we're
Oh.
adding and subtracting. So what does adding or subtracting on the inside do? Left or right? In this case, since we're subtracting, which way are we going? We're going the opposite. We're going right, and we're going right pi. Now, at first you might see that and be like, that's weird, but when you think about graphing sine and cosine, if you look at your scale, it's in terms of like pi and pi halves and things like that. So we're not,
terms of radius.
it's going to be easier for us to do that using measures of pi. It's harder to do it if we use regular numbers, okay? Now this is actually going to be given a new name as well. This is called a phase shift.
Phase shift?
Phase shift. Just like that.
Is it only with pi or is it anything inside the
Anytime that you move it left or right. Okay, cool. So now what we're going to do is we're going to start with basics. We're going to just do one transformation at a time, and then we'll combine them until you guys are graphing machines, right? You just got it, and you're like, boom. Okay?
Boom.
Let's start out pretty easy. Honestly, all you need to know at this point is how to graph sine and cosine, which you guys do. So let's start with just some amplitude changes, okay? When we see numbers multiplying on the outside, those are going to affect the amplitude. When we have numbers on the inside, those are going to affect our period. Now, what we're going to do here, I want to highlight something here, which is going to be this formula right here. You see where period equals 2 pi over b. Will you write that down somewhere on your notes? Period is equal to 2 pi over b. We're going to use that formula here in a second.
What is B?
That is, okay, so that's, b is the number on the inside.
Okay.
So let me show you, without graphing, let's just look at 2 examples here, okay? Let's look at this. Y equals 2 times the sine of 4x. What is the amplitude going to be here? 2, and what that means is this is sine, so sine starts at 0. Instead of going up to 1 and down to -1, this is going to go up to 2 and down to -2. So that just stretches it out. When I'm looking at this one, y equals 1/3 cosine of 2 pi x, the 1/3 is going to make it so instead of going up to 1 down to -1, we only go up to 1/3 and we only go down to 1/3, so it kind of shrinks it down.
So is the b in the equation, or not equation, equation supposed to represent the number in the parentheses?
Well, we're going to get to that right now, okay? So let's look at this one. So b is, yeah, this inside number right here. So here's the parentheses. So b is 4, because you see right here, b is the number inside the parentheses. So if I was looking at y equals 2 sine of 4x, b is going to be 4. So I'm going to take that 4 and I'm going to plug it into this formula for period.
So 2
Period is normally 2 pi, but now we're going to divide it by 4. 2 pi over 4 reduces to pi halves, which is just 1/2. So what just happened, guys, here, is our period is normally 2 pi. But now, it's going to only be pi halves, meaning it's going through 4 times as fast. So when I times it by here, it's actually going to change the frequency or how often it repeats itself. Here we're going through 4 times as fast, okay? Well, actually, let me go over a couple of these more basic ones, and then you'll see them one at a time, okay? Let's go to this one. I'm going to start on number 2. So let's start with sine. I want to just graph the regular plain old one. So Emily, where does sine start at?
Is it 1 or 0?
So sine was 0, yes, because we start at sine. Sine is height, and the height at 0 is 0. So good job. And guys, how long does it take sine to go through a cycle? 2 pi. So when I'm graphing, I always do a start and a stopping point. It always ends where it started from, right? So it starts at 0 and it ends at 0. Now, sine goes up and then down and then back to where it started. So it's going to get to its maximum 1 right there, its minimum -1 right there, and that's one cycle of sine. Now I'm just going to kind of draw a couple more dots,
Because we have.
just so we can like see that a little more clearly. So this is sine of theta. That's our parent function. And as I showed you in the warm-up, I like drawing that before I do transformations just to make sure when I transform it, I get the right ones, okay?
Oh, so would we be moving that? We wouldn't be moving that 4 up, would we?
No. So if we had +4, that's what we did last time. That's where we shifted up 4. But now we're timesing by 4. What did we say timesing by 4 changes? What's the vocab word we just got?
The amplitude?
Amplitude, which is like a vertical stretch. What this is going to do is it's going to make it so that our maximum is now up here at 4, and our minimum is down here at -4. So it's stretching it out.
Oh my goodness.
So basically, I'm going to times all the y values by 4. Now, what is 1 times 4? It's 4. What's -1 times 4? -4. 1 times 4 is 4. So all of those points that were at 1 or -1 get stretched to either 4 or -4.
Oh wait.
Now, what about our x-intercepts? Our x-intercepts are when y is 0. What's 0 times 4?
0.
So our x-intercepts are just going to stay x-intercepts, just like that. So now when I graph it, it's going to follow the same pattern of going up and then down, then up and then down. But notice that it has been stretched out by a factor of 4. That's how you graph it with a change to the amplitude.
So why did the other ones change?
They did. Are you talking about the x-intercepts?
Yeah.
Because here the y value is 0, and what's 0 times 4?
Oh.
Still 0.
Okay, I see. I got confused for a second. I was like, wait, what's going on?
Now, if you think about it, we called this before a vertical stretch. And I'm going to stretch this vertically like that. And that's why the x-intercepts, they stay in place. I'm not stretching it this way, right? They're just stretching away from 0. But if they're on 0, well, then they have to stay there, okay?
Oh, and then vertical would stretch like this. So
Horizontal.
It would stay on 1, but the other one would go
Yes.
farther.
Awesome. Okay, so now I want you to think in your brains. On number 1, what is the amplitude? It's not. What's timesing? It's 1/2.
I thought you were asking.
Louise, what do you think is going to happen if I times by 1/2? It's going to shrink it down. Good job. So instead of going up to 1 and down to -1, we're going up to 1/2 and down to -1/2. So now let's actually just graph this from the beginning,
Oh,
okay?
this is cosine too, so it's gonna
Yep. So let's start with graphing plain old cosine. I think it's good to draw your parent function. So cosine starts at 1. It completes a cycle in 2 pi. So that means halfway at pi, it's going to be at -1. So I get x-intercepts at pi halves, 3 pi halves. So it's going to look like this. Okay, this is cosine. You guys are going to get real good at graphing sine and cosine, right?
Yes.
Awesome. Now we're going to times all the y values by 1/2. And as Louise said, that's going to shrink it down. So instead of being up at 1, now we only make it up to 1/2. And instead of going down to -1, we only get down to -1/2.
Or you,
Now, our x-intercepts are still x-intercepts. So when I graph this, it's kind of like just been shrunken down a little bit. It doesn't get quite as high or quite as low.
it's kind of hard to draw it with the other one because it's like it's so small that it's just kind of squishes in.
Yeah. For me, I have different colors, so it makes it a little easier, and it's a bigger screen. So there you go. Alright, so that, guys, is amplitude. It's just like a vertical stretch. You just take your max or your mins and you stretch them out to whatever the number in front is. Do you have any questions on this amplitude? And I like to label my graphs so that I can tell the difference between them. Alright, so that was amplitude. Let's go on to the next one. You ready? The next one is going to be when we're multiplying on the inside. Now, here's where you got to be careful. That number on the inside is actually going to be the letter B. When we think about that transformation, think of that letter as a B. And this is when we're going to think back to our formula that said period is 2 pi over B. So on number 3, what's the number multiplying on the inside? It's a 2. So in my formula, I'm going to do period is 2 pi over that number here, which is 2. If I have 2 pi over 2, how can I reduce that? The 2 over 2 is just 1, so that just becomes pi. Now, what does that mean if the period is pi? What is a period normally?
It's the end. So
It's
like,
2 pi, right? It's how long it takes to go through a cycle. Well, then if I'm going to make it pi,
It squishes it.
I'm squishing it horizontally. That makes it so it goes through its cycle faster. So I'm actually going to be able to fit in 2 cycles in the time it normally takes me to do 1. So I'm going through twice as fast.
Squishing it.
Squish it. So now let's draw a picture. Alright, so Isaac, when I draw cosine, how do I draw cosine?
You would start from 1.
1. Great. And then I always do a start and stop point. So I start at 1. How long until I get back to 1?
2 pi.
It's normally 2 pi, but for this one,
Well, I thought we're
Wait,
gonna
I'm
graph. You're always graphing it first, and then this one you're not gonna.
I'm not going to do the parent function on this one.
Okay.
Well, okay, fine. Maybe I will.
Well, like, oh
We'll
my
do
God,
the parent function just to make Mindy happy.
Well, I was drawing it, and I'm like, oh wow, you're not gonna do this time, huh? I'll one time I actually draw it.
Okay, so it normally takes 2 pi, which means halfway we're at pi. So here we go. This is what plain old cosine looks like. So this is plain old cosine. Now for this one, well, now I got to give you a second to catch up, so let me count it down. Alright, do you guys have cosine drawn?
Yes.
And the reason, so let me just point this out right now. The reason why I always do a start and stopping point is because your scale changes. Like in this graph, notice how 1 unit is pi fourths. But on this one, 1 unit is pi halves. It can change, so it's good to kind of make sure you're graphing it correctly by doing a start and stopping point. Now, if I'm doing cosine of 2 theta,
I thought the amplitude only affected the up,
it
not
does.
the down.
Oh no, it affects both. It's stretching away from the x-axis.
Okay, so like if with an affects up, it affects down by itself. Okay.
Now, when I'm doing cosine of 2 theta, my period is only pi. I'm still going to start at 1, but when am I done?
Pi.
At pi. That means halfway, it's pi halves, I'm at -1. So 1 cycle is going to look like this. Now let's draw another cycle. If it starts at pi, it's going to end at 2 pi. So there we go. So how many cycles was I able to fit into 2 pi?
2.
2. It normally takes me 2 pi, right? So I like to think of this 2 that I'm going through twice as fast. Okay? Are you guys okay with that example then?
Yeah.
Okay. Let's go to number 4. We're graphing sine, and I'm going to start off by doing just plain old sine. Just because we want people to be happy. I'm not going to do that every time, okay?
Well,
But
I thought you were.
I'm just until we get used to it, okay? But
I was just already drawing it. I was like, whoa, you're gonna pull out and not do it so right.
so here I'm doing sine. Starts at 0.
Oh, this one I was. That's going to 6 pi, not 2.
Yeah, you can already tell just by the scale here.
Like this graph.
So what I've done here is in purple, that's just plain old sine. It has a period of 2 pi, so it finishes once here, and then we get another one there in 2 pi, and then another one there in 2 pi.
Probably didn't use all the buttons.
Okay, so what we're going to do, this one's a little bit tricky, and this is one that throws people off because I say, what is b? What is being multiplied on the inside? And people say, well, nothing's being multiplied, it's being divided.
That's just backwards.
And exactly, it is just backwards multiplication. So I want you to think, don't shout it out if you know. Dividing by 2 is the same as timesing by what? Think in your head. Dividing by 2 is the same as timesing by what? Now shout it out. 1/2, right? So I'm going to rewrite this as, instead of sine of theta over 2, I'm going to write this as sine of 1/2 theta. I'm going to write that in green so we don't confuse our colors. So this is just sine of 1/2 theta. That means b is 1/2, right?
But that's a fraction in the bottom of a fraction.
Yeah, that's going to make some problems here, but let's talk about it. So I'm going to say, so period is 2 pi divided by 1/2.
No.
Oh, fractions
Stop.
within fraction, it's hurting my brain.
Stop.
But guys, we know how to do that. 3 words. What are the 3 words when you're dividing fractions by fractions?
Keep,
Flip.
change, flip.
Keep, change,
But
flip.
the first one is a fraction.
It is 2.
Is it 2 over 1?
Yeah. So 2 pi is just 2 pi over
Big
1.
fraction. It's a big fraction.
And then what is 1/2 flipped over? So keep, change, flip. I keep, change, flip to 2 over 1. What's 2 pi times 2?
4 pi.
Boom. So the new period is 4 pi. What does that mean? So when it was only pi, we went through faster. So if it's 4 pi, what does that mean?
Slow. It's gonna be so wide.
Down. There we go.
It's gonna be
So
so
whereas
hard to draw.
this one went through twice as fast, this one went through half as fast. It's
Oh my
slowing
goodness,
it
Silver,
down.
this is gonna be the longest you I've ever drawn.
Oh no, it's not.
It's what? No, don't say that.
Okay, so let's just kind of start at the beginning, okay? Sine. Where does sine start?
0.
And that's my starting point. How long does it take this sine wave to go through a cycle?
4.
4 pi. So I'm going to put my next dot at 4 pi.
It doesn't even go down until ages. No.
So now that means my halfway spot is 2 pi. So it's going to go up to 1 at pi, down to negative 1 at 3 pi. So here is one cycle. And you can see that it's going through half as fast. Whereas before we were going through twice as fast, now it's like we've already gone through 2 cycles and we just got through 1. And we want to graph to the end, so we're just going to kind of keep going here. It's not going to be able to finish a cycle, but we will be able to at least kind of get in half of one like that. So this green one is sine of theta over 2. So do you see how that kind of slowed it down? It stretched it out horizontally. We call this changes in the period. Now the number here isn't the period, that's b. We divide the period 2 pi by that number. Okay, let me pause there. Do you have any questions on period? Do you feel like you're getting it? Is this making sense?
It makes it hard to draw.
Okay, now what we're going to do is let's combine those, okay? We're going to combine changes to the amplitude and changes to the period. So, looking at example 3, or example 2 here, we've got y equals 3 sine of 4x. I want you to turn to your buddy, and I want you on y equals 3 sine of 4x. I want you to figure out what is the new amplitude, what is that going to change, and what is the new period. But don't graph anything yet. But I want you to figure out what is the amplitude and the period. You got 30 seconds. Go.